hope you're all doing well. Today we're going to talk more about z-scores, and we're going to use the standard normal distribution table, so you need to make sure you take a look at that. So the first part, we're just going to use the z-score formula you guys already worked with, but now we're going to solve for standard deviation. So in this first example, it says, in a normally distributed data set, find the value of the standard deviation if the following additional information is given. One of the things that you guys aren't going to really notice, but you should notice, is that all across all of these problems, it does tell you it's a normally distributed data set, because otherwise we cannot use this kind of information. Okay, so that's just something to notice. Okay, so this first example says the mean is 10.2 and a z-score for a data value of 8 is negative 0.7. So I plug in what I know. My data value is 8. I subtract the mean. It's just that formula you use to find z-score. I divide by a standard deviation, which I don't know, and this is my z-score. Okay, solving. I just do 8 minus 10.2. That becomes negative 2.2. Okay, now, remember, this is division. Opposite of division is multiplication, which would move it over here to be with that 0.7. And then I finish by dividing by that negative 0.7, and I get that the standard deviation is 3.14. Okay, that would be my answer. All I got to do. All right, my next stuff says, if z is a randomly selected value from a standard normal distribution, again, standard normal distributions, you can use the standard normal table to find the probability that z is less than or equal to some given values. Okay, so that's important to understand, that this is always less than, and we're going to look at how that affects our answers sometimes, okay? But you do need to make sure, I've attached this also, this is what we're going to be using. It's there. If you Google standard normal distribution table, you'll get all of these. Okay, so let's look at how we use this table. We want to know how unusual is a z-score of, okay, 2.75. So I go to my standard normal distribution table. I look for the 2.7 part along here. So I get to 2.7, and then for the 2.75, I'm going to come across to where I'm below the 0.05, because that makes 2.75. And I get 0.99702, which is what I wrote here. Remember, we turn that into a percent by moving the decimal twice. So we would say that 99% of the data is below the 2.75. Okay. All right, the next one. I want to know how unusual a z-score of negative 1.34 is. So I go to my standard normal table. I go to negative 1.3. I find it. I scoot over to the 4, so that's negative 1.34. And I get 0.09012. Okay, which I just moved decimal twice. 9% of the data is below it. Okay, last one of this kind, negative 0.37. Okay, so I go negative, I find the 0.3. There it is, negative 0.3. I go over to the 7. I gotta pay attention sometimes, use something to help me keep my line spacing. I get 0.35569. Move the decimal twice. 35.6% of the data is below it. Okay. All right, that's example 1, just the basics of using that standard normal table. Now, we want to sketch a normal curve, then use the table of standard normal probabilities to find the following. So we're practicing just the basics, and then we're going to look at applying this. So this means, what is the probability that the z-score is less than 2.34? So if I look here, I say, oh, that's 1 standard deviation, 2.34 would be about here. And since we want less, we want everything that's below it. So I come over to my z-score standard normal table, 2.34. I say, okay, there's 2.3. Go over to 4. I say, oh, that's 3. 4. 0.99036. Okay, which I rounded to 0.04. Now, it always gives us below, so that's just straight up our answer, 99.04. Okay, on this next one, though, this is where we have to be careful, because this is saying what's the probability of a z-score that's greater than negative 1.76. So I go to my standard normal table. I can fill this out first if I want to help myself. I draw a line approximately where that whole negative 1.76 would be, and since we want greater than that, I shade above it. Come over to my chart, and I say, okay, negative 1.7, I want 1.76, so make sure I'm in the right spot, up 1. I get 0.3920, 0.03920, and I say, okay, now, that's below. That it always gives us this side. So if we want above, we have to take 1, because it's always out of one hole, and subtract that 0.03920, okay? And I would get 0.96 something. And so I move the decimal twice and I say, okay, 96.08% is above that z-score, okay? But remember, that standard normal table always gives us below, so we have to think about what we want. So on this one, we want the probability that the z-score falls between negative 1.28 and 1.04. So if I were going to mark the negative 1.28 here and the 1.04, I'm doing everything between them. So I start by looking up that negative 1.28 on my z-score chart. When I look it up there, I get this 0.10027. Okay, that represents this area below that line. Okay, then I look up that 1.04 and I get 0.85083. That represents everything from here all the way down. So if I want just the shaded region, I'm going to take the whole thing and subtract this. And so I do that, 0.8503 minus that, and I end up getting that 75.06% of the data would be between those. Okay. All right, so you have some problems like that. Go back and listen to this again if you need, or Zoom and ask me for help. All right, example 3. This is where we're actually going to start applying this. Suppose the wait time at a doctor's office are normally distributed, again, that's important, with a mean of 30 minutes and a standard deviation of 10. How many people wait less than 10 minutes? Not 10, 15, silly me. Okay, so my data point is 15 minutes. I subtract the mean, divide by the standard deviation. I get a z-score of negative 1.5. Now, when I look up that z-score, okay, because there's no hundredths place, I just use the negative 1.50 and I get 0.06681, okay, is below that, which means that 6.68% of the patients wait less than 15 minutes, okay? Now, if we want to know how many patients wait more than an hour, I start with the fact that an hour is 60 minutes. Mean time is 30, divide by the standard deviation, we get a z-score of 10, not 10, we get a z-score of 3. I look that up. Now, this is what I get. Now, remember, that's for less than an hour, okay? But our problem said wait more than an hour. So we do 1 minus that to get more than an hour, and I get 0.00135, or about, if I move that decimal, 0.1% wait more than an hour. Now, we can turn this into actual people if we know the number of people visiting. So, if there are 1,500 patients at the doctor's office each week, what does this mean? What this means is, I can take those probabilities I found, that 0.06681 multiplied by the 1,500 patients, and I find out that 100 patients each week would wait less than 15 minutes. Okay, that's what it actually means. I can take the other number we found, multiply by the 1,500, and I can find that 2 patients each week would wait more than an hour. So this is actually kind of interesting. We can predict. All right, last example, and then you guys are going to just do a worksheet for me. So it says, suppose car mileage is normally distributed with an average mean car having 114,000 miles and a standard deviation of 34,000. What percentage of cars have less than 50,000? So I do my z-score calculation. 50,000 minus 114,000 over the standard deviation gives me a z-score of negative 1.88. If I look up that z-score, this is what I get. Remember, it's always less than that, which tells us that 3% of cars have less than 50,000 miles on them. Okay. What percentage of cars have between 50 and 100,000 miles on them? Okay, so we have to find those z-scores separately, just like we were doing before. So I already have the 50,000. Now I'm going to do the 100,000. The 100,000 gives me a z-score of negative 0.412. I looked that up on my standard normal chart, and it tells me that for negative 0.412, 0.34090% of the data falls below it. Now, remember we need to subtract to get between, because this would be the percent that's less than 50,000. This would be the percent that's less than 100,000. So if we want between those two, we simply subtract. So we do that 34.1% minus the 3% we found in part A, and we find out that 31.1% have between 50,000 and 100,000 miles on them. So you're going to practice this for homework. Like I said, if you have questions or need help, please feel free to get a hold of me. Okay, bye.